Right, so here we go with CCEA, A2 Physics, Unit 2, Fields, Capacitors and Particle Physics for June of 2018. Let's get started. Question 3, Part A1. The standard model of particle physics is a theory concerning the four fundamental forces of nature and is used to classify all known subatomic particles that exist. Complete Table 3.1 by naming the four fundamental forces in nature and their corresponding exchange particles. Okay, so this is straight bookwork from your notes. We've got our four fundamental forces: strong force, weak force, electromagnetic and gravitational. And we have our four exchange particles: strong force gluon, weak force W and Z bosons, electromagnetic the photon, and gravitational the graviton. So you've got your four forces and your four exchange particles. Part 2, subatomic particles can be classified as hydrants and leptons. State two differences between hydrants and leptons. So firstly, hydrants are made of quarks and leptons are fundamental. That's the most obvious difference. The other thing is that hydrants, because they're made of quarks, can feel a strong force and leptons can't. Okay, and state the quark structure of the neutron. Well, if you think about your up quark has a plus 2/3 charge and your down quark has a minus 1/3 charge, and protons and neutrons are made of these. You see that to get a neutral particle you need two downs and one up. So it's going to be U, D, D for a neutron. Part 4 then. State the equations which describe beta decay in terms of quarks. Include the virtual exchange particle emitted. So remember that we're going U, D, D, neutron, to U, U, D, proton. So what's happening is that one of them, this middle one, is changing. So the quark decay is U, oh sorry, I've got that back to front, is D going to U, and then when this happens you get a proton appearing, but you also get an electron appearing. So there's a negative thing happening, so we get a W minus particle, and that W minus particle then decays to an electron and anti-electron neutrino. So we end up with a proton being formed, and we end up with an electron as well, so the whole thing conserves charge. And that's why the exchange particle has to be negative, because it has to conserve charge at the first equation as well. So this has to conserve charge, and what has happened is that we've got an increase of +1, so we have to have a minus sign to cancel that, and then that minus thing decays to a minus thing here. Remember that the antineutrino is an uncharged particle. Part B. Consider two appropriate conservation laws to determine whether the hadron reaction described in equation 3.1, which produces a pi minus meson, can occur. Okay, so we've got our conservation laws, and we look at each one. So we'll look at, say, for example, the conservation of charge. And you can see we've got 0 added to +1. So we've got a total of +1 on that side. And we've got 0 added to +1 again. added to another +1, added to a -1 for the pi. Okay, so we've got a total of +1 on one side, total of +1 on the other side, so it does conserve charge. Now we could go lepton number. Okay, so the neutron has no lepton number, the proton has no lepton number, the neutron again has no lepton number, the proton again has no lepton number, the other proton has no lepton number, and the pi meson has no lepton number. So that conserves. And then we could look at baryon number. So the neutron has a baryon number of 1. The proton has a baryon number of 1. So we've got a total of 2 there. The neutron on the other side has a baryon number of 1. The proton has a baryon number of 1. The other proton has a baryon number of 1. And mesons all have a baryon number of 0 because they have a quark-antiquark. Okay, so we've got 2 on this side going to 3 on the other side. So that is broken at baryon number, and the answer is no. And just maybe indicate here with a little header that you're checking whether or not these things are being conserved. And that's it. Thanks for watching.